Thank you so very much, Pierre. Thanks to all the organizers for having invited me to present my research here. And I would also like to thank to the many collaborators that have made this research that I will present today possible. So I would like to start with a very quick digression on terminology, what we understand by volcanic hazard and what we understand by volcanic risk. So volcanic hazard, classical definition could be the probability of a given volcanic hazardous phenomenon to occur in a given point in space with a given intensity and within a given time window. And if we were talking about volcanic risk, we were talking about the probability of a given loss in terms of human lives or economical or others related to volcanic activity to occur in a given point in space and within a given time window. So if we turn these two definitions into examples, we could have that volcanic hazard could be the probability of a pyroclastic density current, which is a very complex phenomenon that I will show right after this slide, to occur 10 kilometers away from Mount Pinatubo in the Philippines as our point in space, traveling at 60 kilometers per hour as our hazard intensity measure during June 1991 as the time window. And volcanic risk would be the probability of one or more casualties related to that PDC to occur 10 kilometers away from Mount Pinatubo during June 1991. So here we are, June 1991. This is the pyroclastic density current, which is basically a multi-phase, multi-component, fast-moving, very hot flow of volcanic particles and gas, which propagates away from the volcano, as I said, at very high speed. So the destruction potential that this phenomena has is very high. So the hazard is very high. And given that we have this little truck over here trying to get away from the PDC, risk is also very high. But if we remove the truck from the scene, hazard is still very high because the phenomenon is there. But given that the truck is not there anymore, our volcanic risk has significantly decreased. So what happens with volcanoes is that they're very versatile and powerful threats. So they have many different ways in which they can cause harm, from burning, poisoning, asphyxiation, burial by sediment load, cascade effects, etc. So we have just seen the pyroclastic density currents, which is one of the ways these phenomena are formed, is basically by the collapse of this eruption column, which is the mixture that is being erupted from the vent in the case of explosive eruptions. This mixture, when it exits the vent, is more dense than the surrounding air. So if it's not able to entrain enough surrounding air and heat it in order for it to become less dense than the air, it would collapse and generate these pyroclastic density currents, also known as pyroclastic flows. If the mixture is able to entrain air and become less dense than the air, than the surrounding air, it would basically rise vertically to a point in which its density will re-equilibrate with that of the surrounding atmosphere at a given height. And at that point, that cloud would be basically spread out laterally following the prevailing winds. And one phenomenon that is associated with this process is the tephra fallout. So it's basically this rain of volcanic particles back into the ground, and that can cause problems such as collapsing of rooftops, for instance, of buildings due to the load caused by these volcanic particles. We have other phenomena like lava flows, which are very famous in Hawaii or in Mount Etna in Italy. And we may have other phenomena such as the partial collapse of the volcanic edifice. And one of the problems, and we'll talk about this later on, is that many of these processes can occur contemporaneously during a given eruption or a given eruptive phase at a volcano. So we need to account for that, as we will see later on. Volcanoes, as other natural phenomena, if we look at the fatalities related to volcanic activities from 1600 up to 2010, we see the red curve is the cumulative number of fatalities over these 4 centuries period. And similar to other natural phenomena, this curve is kind of stepwise. So there are some very large disasters which are associated with a large number of fatalities, and then in the middle there's kind of a more horizontal pattern in this curve. But if we remove this, well, I would also like to add that there's been other disasters in 2010, like Fuego in Guatemala and Krakatau in Indonesia. So unfortunately, we keep seeing this kind of disasters related to volcanic activity. And the thing is that even if we remove the largest disasters, so the blue curve is removing the five largest disasters, the purple curve is removing the 10 largest disasters, even when we remove them, we have kind of an average trend of 200 deaths per year approximately. So it's a number that we cannot forget about. It's an important number that we need to remember and act accordingly. So another factor is that the exposure to volcanic activity is ever increasing because we tend to build closer and closer to active volcanoes. And we will come back later on to the city of Napoli in southern Italy, mainly surrounded or built on two volcanoes, Campi over here and Vesuvius over here. But there are other cases like in Japan, Shimabara City and Mount Unzen, and Ecuador's capital Quito and the Huavo of Chincha volcano. So we see there's high exposure to volcanic hazard. And the thing is that volcanic hazard, the impacts related to volcanic activity are not only local or regional, they can also be global. So this is the example of the 1815 eruption at Mount Tambora in Indonesia. The year after that eruption was known as the year without summer. And here in this map, we see the negative anomaly in temperature all over across Europe, especially in France, related to the presence of a large amount of volcanic particles in the atmosphere, which increased the albedo effect, so the amount of sunlight that was reflected back to the atmosphere, causing this cooling effect in the Earth's surface. So if we want to quantify hazard, one of the problems that we have is that the uncertainty is very high. And so we have also different sources of uncertainty. So if we want to quantify the probability of pyroclastic density currents, for instance, to impact this point in space in the city of Napoli, first of all, we're faced with aleatory uncertainty, so related to the natural variability of the system. We don't know when the volcano may erupt. We don't know from where the volcanic activity may be sourced. We don't know how big the eruption may be, etc. But we also have sources of epistemic uncertainty related to lack or incomplete knowledge. So we may have scarce data, or data maybe of different qualities, spatial distribution, etc. We may have different models to use in order to quantify hazard, and of course, all models are representations of reality, etc., etc., etc. So one way of trying to capture these two main sources of uncertainty into our hazard assessments is to model the frequency of PDC arrival at this point as an uncertain variable, so we can attach a probability density function to this variable. And so a single value of the variable, for instance, a central value of the distribution, like the mean or the median, it's a measure of aleatory uncertainty, but the whole distribution, for instance, the dispersion of the frequency of PDC arrival around this central value is a measure of epistemic uncertainty. And now we'll move into some specific challenges that I think are relevant at the moment in volcanic hazard. So a first challenge is that we are scarce in terms of data at many volcanoes worldwide. And here I'm showing the data for 1,500 volcanoes in a global database of volcanological data. In black, I'm showing those volcanoes for which we have information about the sizes of past eruptions in the system. And in red, I'm showing those volcanic systems for which we don't have such information. And this is over the last 12,000 years, more or less. So we may think, okay, we have a lot of areas that are well covered with volcanoes with information about past eruptions of the system. But it's just a trick of how I have plotted the data. First, I plotted the red data, the red points, and then I plotted the black points on top of that. If I do the other way around, we start seeing how it's actually up to 50% of the volcanoes worldwide don't have information about the eruption sizes of the past eruptions. So that's a big problem that we face. And so one of the things that volcanologists are trying to do is to see if there are some similarities among volcanic systems, so we can borrow data from volcanoes that are data rich into those volcanoes that are data poor. And so it's a matter of trying to see if we can extract the similarities between different volcanic systems, because depending on the scale that we look at volcanoes, volcanoes may seem unique. This is just 5 examples. So each volcano seems unique, but we know that there are some patterns in volcanic activity that may make some volcanoes more similar to others and more different to others. And later on, I'll be talking about Stromboli in Italy and Eluto in Ethiopia, just as an example. But basically, the idea behind using analog volcanoes, which is the term that is used in volcanology to refer to volcanoes that are similar enough as to be considered partially exchangeable. The idea is if we had an unknown person and we wanted to say something about the height of this person, if we knew it was a woman, then we could take all the women as analogs to our unknown person, measure their height, and come up with a distribution of the height for this unknown person. If we knew that our unknown person is Belgian, and I checked that apparently Belgian women are taller than the average worldwide woman, we could treat all the Belgian women as analogs and compute a different distribution, which would be shifted towards higher values of the variable. And if we knew that our unknown person was a WNBA player, so a professional basketball player, we could treat all those players as analogs, measure their height, and come up with a distribution that is clearly much more shifted towards higher values of the variable. So similar with volcanoes, one of the ideas of trying to assess and to identify analog volcanoes is we have a volcano for which we don't have enough information, but if we were able to assess that it's similar to a Stromboli, we could take all those volcanoes that are similar to Stromboli and compute a distribution of eruption size that may look something like this. But if in turn it was more similar to a Luto, we could treat all the volcanoes similar to a Luto and compute the distribution for the eruption size of our non-volcano that may look like the red curve, for instance. So what we did with this method, which is called Volcans, which stands for Volcano Analogs Search, what we did is using global volcanological databases and look for criteria that allowed us to assess the differences and the similarities between volcanoes in a way that we could then see which volcanoes in the database were most similar to a given target volcano that we are studying. And I'm not going to go into all the details of the method, but you can check the paper, which was published last year. But here I'm just showing the example of Volcán de Fuego as a possible target volcano in Guatemala. Some criteria that we are using is, for instance, the morphology, because the morphology of the volcanic edifices tells us about similarities and differences between them. We can look at the composition of the erupted products, because different chemistries at different volcanoes tells us about which are more similar or more different to each other. And of course, we can also look at the type of volcanic activity of our target volcano. And again, some volcanoes will be more similar or more different to others depending on the type of volcanic activity that they have. So the final goal is to go from all the 1,500 volcanoes, in the database to those volcanoes that are most similar to our target volcano, following the criteria that I have just explained. And so that's the way we can, for instance, this is an example of the top 20 analog volcanoes to Fuego. So those that have the most similar characteristics to Fuego. And what we can do then is to compute distribution of eruption sizes. This volcanic explosivity index is a metric very, very widely used in volcanology. So we can take our top 20 analogs, sample their distributions of eruption sizes, combine the sample into a unique distribution, and use that distribution for our data per volcano. In this case, Fuego is not data poor, so we have also information for it, but it's basically a way of checking whether the distribution that we obtain from the analogs is similar to the distribution on the left-hand side, which is basically the distribution that you obtain using the data for Fuego in the global databases. Another, just a sec. Sorry. Another challenge that we have is that the most dangerous phenomena are usually the most complex as well. So we're talking about pyroclastic density currents before, and these very complex flows. Thing is that they are multi-phase, they're multi-component. The particles that they can carry vary in size from several meters in diameter to microns in diameter. They are stratified in terms of concentration vertically. They're stratified in terms of velocity. Additionally, without going into all the detail of this slide, basically the generation mechanisms of these flows are very complex and very varied. So that implies that the source conditions of these flows are very variable. So the aleatory uncertainty in the PDC triggering it is very high. And on top of all this, basically these complex flows interact with real 3D topography in very complex manners. So here is just an example from Mount Pelée in Martinique. But it's basically, and it's just a transect kind of cross section of the topography. But we see how the PDC is sourced here, it interacts with topography. Part of it can become less dense than the air and lift off. Parts of the current can decouple and resegregate a dense basal part, etc., etc., etc. So the thing in volcanology related to PDCs is that we have a range in numerical models or physical models that try to model the process that range from very simple to very complex. The very simple allows us to quantify uncertainty and estimate hazard much more easily, and some of the very complex are so complex that the runtimes don't allow us to compute uncertainty at all. But of course, complex models capture the physics better than simple models. So we are faced with this dilemma. And here I would like to just show a small example about simple versus complex models. Here we have Kepler's second law on the left-hand side and a very complex multi-sphere model to represent the Earth. And the question is, what model is better to describe the Earth? And I guess my answer would be it depends. If we're looking at a quantity of interest like the position of the Earth XYZ in 2050, then perhaps we could obtain a reasonable estimate with the simple model. But if we were looking at estimating the mean ocean temperature at the surface in 2050, then of course we couldn't use the simple model and we would need to use the complex model on the right hand side. So what we did for PDCs was having a look at the very simple models because we could quantify uncertainty easily, even in a Monte Carlo scheme in which we ran millions of simulations of this very simple empirical model, which just has two parameters, the collapse height from which the PDCs are generated, and a parameter that basically describes the mobility of the flows. So the question behind this was, if we quantify the aleatory uncertainty for a given volcanic system, and we try this at Vesuvius and Campiferae in Italy, so for the two parameters, we attach probability density functions for the parameters, trying to simulate the aleatory uncertainty in the PDCs that may be generated at these volcanoes, different eruption sizes. If we assess this uncertainty, sample these distributions, and propagate this aleatory uncertainty by using the model, then are we able to reproduce past measurements from PDC deposits in terms of the maximum runout of the flows and the area of PDC invasion as two of the kind of first order metrics in terms of hazard? And so what we did was doing that, and we had several PDC deposits available, and we computed different metrics, but one of the metrics that we computed was the aerial field, so basically the division between the intersection area between the simulation and our PDC deposit, and the union area between these two polygons. So basically, the aerial field goes from 0 if the two polygons are completely separated to 1 if they are perfectly equal. And what we saw is that this is just one case for Mercator eruption at Vesuvius. One of the things that we saw is this our parameter space, and in colors the values of the aerial fit for Mercator. We saw that we found some high values of aerial fit, but also low values of aerial fit related to either higher or smaller events compared to the ones that we have in the record. So that was a good result to obtain events that were similar but also larger and smaller, because we were trying to quantify the aleatory uncertainty of our volcano interest. And on the other hand, when we look at the two volcanoes and 24 eruptions, we're showing here the best aerial feed computed for each of these cases, and I'm showing the histogram. This is the range of values of best aerial feed that have been published in the literature for other volcanic mass flow models, more complex, of course, than the very simple one that we have used. So we see that our very simple model has similar or higher values of this best aerial fit. We also wanted to assess what was the impact of epistemic uncertainty for this simple model. So what we did here in the solid curve, I'm showing the model output. So in this case, the area of PDC invasion and the empirical cumulative distribution function. The solid line represents the aleatory uncertainty for the large size, so as we were seeing before, and the other cumulative distribution functions show different assumptions, in this case, in terms of the possible relationships, direct or inverse, between the model parameters. So this is one of the sources of epistemic uncertainty that we explored, but we explored four of them, some of them related with the spatial resolution of the digital elevation model that you use to run your model, and other sources. And in different colors, you can see the impact of each source of epistemic uncertainty. So in this way, we were able to rank the different sources of epistemic uncertainty. And also we checked that all sources of epistemic uncertainty were able to significantly modify the output distributions for the model, both in the case of area of PDC invasion, as I'm showing here, but also in terms of the maximum runout. So with all this information already collected from these two previous works, what we did is to move into computing the probabilistic volcanic hazard assessment from pyroclastic density currents at the two volcanoes. So this was an innovative approach in volcanology to consider, instead of one volcano, only two volcanoes and one target area, which was basically the city of Napoli and surroundings. So we incorporated the simulations that we have from our simple model with volcano-specific data in terms of long-term probability of eruption, distribution of eruption sizes, etc. And we combined it into a probabilistic hazard assessment, in this case, constraint in terms of the temporal window. So in the next 50 years, this is the probability of pyroclastic density currents from at least one of the two volcanoes, assuming that they erupt independently, to impact each point in space in our hazard domain. And given that we were saying that we treat the frequency of PDC arrival as an uncertain variable, so we have a probability density function at each of the points around on our grid across our hazard domain. So here we are showing the map corresponding to the aleatory uncertainty, but we can also compute maps for different percentiles of these probability density functions, and we start seeing for lower and higher percentiles how these maps of the probability of PDC arrival in the next 50 years look like at the area. And the third challenge that I would like to talk about, I already introduced it before, is that volcanoes are strongly multi-hazard. So we need to account for that. We have talked about before tephra fallout from the eruption cloud that is dispersed by the winds. And this one hazard. We have talked about pyroclastic density currents, and that's another hazard. But the thing is that these processes, what they do is they deposit large amounts of pyroclastic material, so particulate material from volcanic origin, around the volcano that is or has erupted. So what happens, and this is shown in gray over here, all that area has been covered by pyroclastic material that then is easily erodible, for instance, by high intensity or long duration rainfall events. And that's where our third hazard comes in, which are these lahars, which are water sediment flows, again, similar to pyroclastic density currents, very complex rheologically, and they can carry particles or blocks from tens of meters into all the way up to microns in terms of the diameter of the particles that they carry. And one of the things related to lahars is that they have very high sedimentation rates. So in the top row, I'm showing two images for Merapi, and on the bottom row, Merapi in Indonesia, and on the bottom row, Pinatubo in the Philippines. On the top row, after 3 months of repeated lahar events, we see how the channel here has completely filled up to the bridge level. But the thing with the bottom row is that one single lahar event was able to deposit several meters of volcanoclastic sediments. And of course, these flows are extremely dangerous. So what we tried to do, without going into all the details of this framework, we wanted to provide a probabilistic framework that incorporated the volcanic hazard interaction. So in short, basically the yellow shows physical or statistical models. The white shows data, source of data or information, and the green is our output, our probability hazard assessment. But simplifying, on the one hand, we have the lahar trigger inside, so we want to explore what are the rainfall conditions to trigger these lahars. And then we also want to assess the volcanic hazard interaction, so how the occurrence of pyroclastic density currents and tephra fallout influence then the occurrence of lahars, given that the material that lahars use comes from the PDCs and tephra fallout. Then we have a part that is using a numerical model to simulate lahar propagation. And by combining the two parts of the model, we can then obtain the probabilistic lahar hazard, which incorporates the volcanic hazard interaction. And that's the part that I would like to focus on right now. We try to assess the aleatory variability for PDCs and tephra fallout and incorporate it into a Bayesian belief network, which is the model that tries to assess the probability of lahars of different volumes. And so, as I show here, I hear some sound there. I don't know if some of you are muted, but I hear some clicking. Anyway, so basically what we want to do is to assess the aleatory variability in terms of the volume that may be available at a given catchment around the volcano due to deposition from tephra fallout and pyroclastic density currents. So we model this process and compute this aleatory uncertainty in terms of the availability of pyroclastic volume at different catchments. And we do it for all these catchments here in blue, and then I will be talking about these two, 195 and 277, highlighted in yellow. And the other colors in the map here show the expected tephra load related to a large eruption, which is the scenario that we're exploring here in this configuration of the BBN. And so you see here how the main dispersal direction of the wind in the area is west-east. So that, of course, will influence, as we'll see now, the amount of material that is expected in 277 compared to 195, even though their areas are very similar. So in the BBN here, without going into all the details, all this part over here, which we have fixed for this example, but it basically is concerned with trying to understand which are the triggering factors for our lahars. This node over here is the lahar volume, so we have probabilities for different lahar volumes, including the no event. And here I just show low, medium, and high, but they're related with thresholds in the values of volume. And similarly, in this case, for the pyroclastic volume. So what we have done by modeling tephra fallouts and PDCs is parameterizing this node over here, which looked at the pyroclastic volume. And as I said before, if we look at the variable here, between 195, the probability of medium or high volumes to be stored in these catchments are quite low compared to 277. And of course, that cascades into the probability of lahar volumes, medium and high, for instance, in 195, which are clearly smaller than in the case of 277. So these are the things that we can assess with these Bayesian networks that we built at each catchment. And then we can use the Lahar simulator. Basically, we're here back at the edifice of Sama Vesuvius. This is the vent and this is the cone. Well, all this area over here. And what we have done here is from each of the catchments, we have simulated a given volume for which it has associated a probability of occurrence given our Bayesian belief networks. And so we model this initial volume using the numerical model for Lahars, and we can compute hazard footprints, for instance, for the Lahar flow speed, which are the colors that I'm showing over here. And so, as I said, given that we have the probabilities for the volumes from the BBNs, with some assumptions, we can compute probability and attach it to this particular scenario in terms of the Lahar flow speed expected around the volcano. And so moving into future opportunities related to the three challenges that I have described. First opportunity may sound very simple, but it's very, very important for us. And it's basically increase the amount of data that we have available. So we need to collect more data and to assemble more data into databases so we can improve our quantitative hazard assessments. And here's just an example for a recent project in Ethiopia. We basically have to go have a look into the deposits, and thanks to that, we can then move into interpreting what past eruptions of the volcanic system may have looked like, and of course, that will influence the way we quantify the hazard and the way we set up our models to quantify hazard. So it's very, very important that we get more data. Another way of obtaining more data is through citizen science. I know that some of you have experience in the field. Here is just an example of an application that was developed at BGS, the My Volcano app, and I refer you to Kate Simi and Melanie Duncan at BGS if you want to more details about the app. But basically, here's an example from the Christmas 2011 eruption from Iceland. The application was used to collect data about the possible presence of ash across the UK, and that was very valuable to then constrain the way the propagation of the plume, of the volcanic plume, was modeled from Iceland to the rest of Europe or other places towards Greenland, for instance. So that data was very valuable. A second opportunity, and that's an open question, is whether we are able to simplify our complex models. Here's an example of a model that back in the day took basically 1 week in a very powerful supercomputer to run one simulation. Perhaps now the runtime has been reduced, but still it's a very long runtime if we want to quantify uncertainty using this model. So my question is, are we able to simplify this type of models in a way that we can keep the main physics inside the model, but we can make the model fast enough as to allow us to quantify uncertainty? And the final opportunity is related to the multi-hazard side of volcanic hazard. In general, there's been a lot of hazard summation approaches in the literature, but very few hazard interaction approaches I have just shown in the case of Lahars. And these are 10 possible hazardous events that can occur at volcanoes and possible interactions between of them. So it's a very, very complex system when we're trying to quantify those. And I just wanted to stress as well that some of the relationships may be unexpected. So for instance, the presence of lava flows on top of deposits that could otherwise be eroded would change the erosive pattern at a given volcano of interest, as it was observed in Mayon, Philippines in 2006. So the presence of lava flow hindered the erosion of the material that was located just beneath that lava flow. And so in other areas where the lava flow wasn't present, there was much more erosion by the rainfall. So I guess my suggestion is to keep using more and more probabilistic graphical models, and I just throw there an invitation to use statisticians to let us know what would be the best way to go through this. In volcanology, we have used a lot of event trees. I haven't talked about this, but there is a certain amount of work that has been done for event trees, a little bit for Bayesian networks, and a little bit less for Markov chains models. But yeah, just leave it there as an open question. Yeah, what would be the best strategies to move forward into quantifying volcanic hazard interaction? And with this, I think I have finished. Merci beaucoup pour l'attention. And if you have any questions or comments, I'll be very happy to answer them.
Okay, thank you very much, Pablo, for this very interesting talk. Do we have any question? Okay, you can just open your microphone and ask your question if you have any, or even write your question in the chat. Okay, so maybe I can start. Yes, so if I understood well, you have these different hazards. It seems that there are 10 hazards, and so you are able to provide a hazard map for any kind of hazard for a given volcano. Am I right?
So what is being used, I mean, this is just 10 examples. Can you hear me properly?
Yeah, yes.
So what is usually done is basically provide hazard assessments for the single hazard. So say we look at PDCs as we've seen before, or we look at surface fallout individually, or lava flows, or ballistics, which is basically projectiles, bombs that are thrown and follow projectile trajectories, etc. But it's commonly, very, very commonly, is focused on the single hazard. And then some people may combine these hazard footprints for the single hazard in different ways. So, but they're not assessing the interaction between hazard, but they just combine them. Sometimes you can combine them, perhaps, if you move into risk and you have a common measure that could be a given loss related to the different hazards. Then you can merge the hazard footprints more easily in the risk to merge your outputs. But in other cases, it's just some people just say, okay, in this point in space, I have hazard footprints for hazard 2, 1, and 4, say. So I'm gonna call this zone 1 because I have 3 hazards that are impacting that point in space, and then another zone where I have only 2 hazards, and I call that zone 2, etc., etc. But that's without quantifying the interactions. It's just kind of summing up somehow. And I'm not, very defendant of this approach, because sometimes it gives the idea sometimes that those areas with 3 hazards are more hazardous than areas with just 1 hazard, for instance, right? But if you think of PDCs versus an area of, I don't know, lava flows and surface fallout, perhaps only having PDCs in an area is more dangerous. It's more risky at the end of the day than having surface fallout and lava flow in a given point in space. And that depends, of course, at the distance that you're located from the volcano. So there are several factors that are not being considered in those approaches.
And actually, the simple computer model cannot account for the interaction, because you say you have some computer model to assess this hazard and a computing hazard map, but usually a computer model is only I guess at least the simple one are only done to assess one kind of hazard and not a combination of hazards. That's why it's really hard to. But
yeah.
Yeah, but in the complex models that you said that it could last a week to have a run. In this case, I guess this kind of model you will be able to have the 10 kinds of hazards from the output of a single model, maybe.
No, I mean this hazard. I mean this model is just looking at the PDCs.
Okay,
so just looking at the PDCs. The thing is that most of the models, what they do is assume they model the source conditions in a less realistic way. While this model, what it's doing, if you remember of the first slides, you have the eruption column that is going upwards. And if it's not able to become less dense at the surrounding area, it collapses to the ground and propagates as a pyroclastic density current. this model is looking at this whole process. The material is ejected vertically. It cannot become buoyant, and it basically collapses back to the ground. And you model how this flows propagate onto real topography, 3D, etc., etc. But you're looking at just PDCs here,
Okay.
so it's just a single hazard. But yeah, I mean, in order to quantify multi-hazard, you need to think of different ways of looking at the problem. That's what we tried to do with this approach, was saying, okay, we're going to model this process and we're going to model this process, and that allows us to quantify the letter uncertainty in terms of the volume that's stored in each catchment. And given that lahars are dependent on how much volume there is and where it is located, as we saw here, then that's how we quantify our interaction between hazards, because there's a clear spatial dependency on the lahar occurrence, depending on where tephra fallout and PDCs have left their deposits. You know what I mean?